A storm lashed the Aegean Sea in the year 1900. Beneath the waves, sponge divers found more than treasure. They found a mystery that would shatter our timeline of human invention. This is the story of the Antikythera Mechanism, a 2,000-year-old bronze computer discovered in an ancient shipwreck. By the end of this journey, you will understand why this single artifact forces us to rewrite the history of technology itself. We will uncover who might have built such a marvel and explore the haunting reason its secrets were lost for over a millennium. How do you think our modern world would be different if this ancient knowledge had never faded away? Elias Stadiotis broke the surface, gasping for air in the churning sea. In his hands, clutched tight, was not a sponge but something far more impossible: the green, barnacle-encrusted arm of a life-sized bronze statue. The crew on the boat stared in disbelief. Their world was one of simple harvests from the deep, not lost masterpieces. The initial reports from the divers were even more unsettling. They described seeing a heap of human forms resting on the seafloor, a vision that filled them with a deep sense of solemnity. What they had actually found, of course, were not individuals but the silent, sculpted forms of ancient statues, toppled together by centuries of currents. The salvage operation that followed was a race against time, depth, and danger. Funded by a passionate Greek government and the royal family themselves, it was one of the first major underwater archaeological efforts in history. The divers, using only those early, heavy suits and helmeted diving gear, worked at the very edge of human endurance. They battled strong currents and the crushing psychological weight of the deep, a hardship underscored when one member of the team did not return to the surface. The price of discovery was steep, and in the frantic recovery of gleaming marble and bronze, many smaller items were left behind in the murk. Among the overlooked pieces was a single, unassuming lump of corroded material, about the size of a large book. It was caked in sea deposit and hardened clay, and it hardly seemed worth notice next to a heroic statue or a delicate glass bowl. This forgotten chunk, hauled up with the rest and stored away with the other minor finds, held a secret that would take another half a century to fully reveal. While the world marveled at the visible art, the true treasure sat quietly in a crate, waiting for its moment to rewrite everything we thought we knew. For decades, the strange lump from the shipwreck gathered dust in a museum storage room. It was officially logged as a piece of rock or perhaps a heavily corroded sculpture fragment, nothing more. The year was 1902 when a curious archaeologist named Valerio Stais decided to take a closer look. He was examining the collection, likely hoping to match broken statue pieces, when a glint of green bronze caught his eye. Peering at one of the nondescript lumps, he saw something that should not have been there: a perfectly formed, tiny gear wheel, its triangular teeth still visible after 2,000 years under the sea. In that single, electrifying moment, the object transformed from a piece of rock into a profound historical anomaly. The initial theories that swirled around the find were a testament to how utterly it defied expectation. The most logical guess was that it must be an astrolabe, a known device from later periods used for navigating by the stars. But even a simple astrolabe didn't require a complex gear train. Others, looking at the intricate interlocking wheels, ventured a more shocking idea: perhaps it was a kind of clock. This suggestion was met with immediate and forceful dismissal from the academic establishment. Everyone knew the mechanical clock was a medieval invention, appearing in European towers around the 1300s. The idea that ancient Greeks, from a time before even the Roman Empire reached its height, could have crafted such a thing was considered not just unlikely, but laughable, a fantasy. The very concept threatened the established narrative of human progress, so the mechanism was quietly sidelined. It was too complex to be an astrolabe, yet too ancient to be a clock. With no comfortable category to place it in, and its secrets locked beneath a thick, stone-like crust of marine limestone, it was easier to label it an oddity and move on. For half a century, it remained a frustrating enigma, a ghost from the past that whispered of impossible knowledge. The gears were visible, but their purpose was utterly obscured, both by physical corrosion and by the limitations of contemporary thought. The true scale of the mystery was still buried, waiting for a new generation of thinkers and, crucially, a new kind of light to see through the stone. The true nature of the artifact only began to emerge when technology finally caught up to its ancient maker. In the 1970s, a team led by a physicist named Derek de Solla Price applied a revolutionary new tool, X-ray imaging, to see through the centuries of hardened corrosion. What the X-rays revealed was not just a few gears, but an entire miniature cosmos of mechanical engineering. The surviving 82 fragments, painstakingly pieced together, represent perhaps only 1/3 of the original device. Inside a wooden case the size of a thick encyclopedia, they found a labyrinth, at least 30 separate bronze gears, some with as many as 223 perfectly formed triangular teeth, all designed to interlock with breathtaking precision. This was not a simple calendar, it was a machine of profound intent. The front and back faces were covered in finely graduated circular scales and moving pointers, and everywhere there were inscriptions, thousands of tiny Greek letters etched into the bronze, a user manual from the ancient world. But the most shocking discovery was hidden deep in the gear train. The mechanism employed a concept called differential gearing. To understand its significance, think of the axle on a modern car. It allows two wheels to rotate at different speeds while still receiving power from a single engine, a necessity for turning corners. In the Antikythera Mechanism, a similar, brilliantly conceived assembly of gears performed a celestial function. It could mathematically account for the irregular orbit of the moon, a subtle wobble in its path known as lunar anomaly. This single feature is what shattered the timeline. Before this discovery, the earliest known use of a differential gear was in the 16th century in European clockwork. Yet here it was, fully realized inside a device that sank beneath the waves before the birth of Christ. The engineering sophistication is simply unparalleled for its era. Every gear ratio, every calculated tooth count, was a deliberate choice to model the observed patterns of the sky. This forces the unavoidable question: what kind of mind or community of minds conceived of such a thing over 2,000 years ago? To answer that, we must move from the gears themselves to the purpose they so elegantly served. The true genius of the device lies not in its gears, but in what those gears were designed to show. This was in every sense a portable cosmos. By turning a small hand crank on its side, an ancient user could set the mechanism in motion and watch as the heavens themselves played out on a series of intricate bronze dials. The front face was a masterpiece of information. One pointer showed the position of the sun against the backdrop of the constellations of the zodiac. Another, more complex pointer displayed the phase and position of the moon, accounting for its subtle speed variations with that astonishing differential gear. Researchers reading the tiny inscriptions found it even named the major stars that would be visible on any given date. This was a dynamic, moving map of the sky for any day you chose to set. But the back of the device is where its predictive power becomes truly staggering. Here, spiral-shaped dials tracked longer, grander cycles. One dial was a sophisticated eclipse predictor. It didn't just show when an eclipse might happen. It used a system of inscriptions to forecast the color, direction, and even the potential weather associated with the event, based on ancient astrological traditions. Another remarkable dial tracked the 4-year cycle of the Panhellenic Games, including the Olympics. This connected the celestial clockwork directly to the sacred rhythm of Greek cultural life. Perhaps most mind-bending of all, evidence strongly suggests that additional, now lost, gear trains on the back were dedicated to modeling the complex, looping paths of the 5 planets known to the ancients: Mercury, Venus, Mars, Jupiter, and Saturn. To replicate their irregular retrograde motion, where planets appear to slow down and move backwards in the sky, would have required an even more sophisticated level of gearing. This transforms the mechanism from a mere calculator into a profound philosophical object. It physically embodies a core Greek belief that the universe operates not on the whims of gods, but on elegant, predictable mathematical principles. You could hold this principle in your hand, turn the crank, and see order emerge from chaos. The very existence of such a device implies a radical idea for its time, that the mysteries of the cosmos were not just for priests to interpret, but could be understood, modeled, and predicted by human reason and craftsmanship. So who, in that ancient world, possessed the knowledge to dream such a thing into being, and the skill to make it real? The silent bronze gears found their voice through the words etched upon them. Covering every available surface of the mechanism's plates are thousands of minuscule Greek characters, each one painstakingly engraved by hand over 2 millennia ago. This is not random decoration, it is a comprehensive user manual from antiquity. For decades, these inscriptions were obscured by corrosion, a ghostly script waiting to be resurrected. The task of reading them fell to specialists called epigraphers, experts in ancient writing. Using advanced imaging techniques like 3-dimensional X-ray scanning, they have slowly, letter by letter, brought this ancient text back into the light. What they have decoded transforms our understanding of the device from a mere machine into a window into a sophisticated scientific mind. The inscriptions serve multiple, brilliant functions. They are, first and foremost, labels. Next to pointers on the dials, you find the names of celestial bodies, the constellations of the zodiac, and markers for key phases of the moon. But they go far beyond simple identification. One set of texts, known as a parapegma, is a star-based calendar. It links the rising and setting of specific constellations with seasonal weather predictions and the optimal timing for agricultural activities. The inscriptions might note, for example, that when the constellation Orion rises at dawn, one can expect winds, or that the appearance of Virgo signals the time for harvesting grapes. This connects the celestial mechanics directly to the rhythm of life on Earth, blending astronomy with practical necessity. The language itself is a crucial clue. The technical terms and phrasing used are consistent with those found in Greek astronomical texts from the 2nd century before the Common Era. This linguistic fingerprint helps pin down the mechanism's origin in time and places it firmly within a specific intellectual tradition. These words confirm the device's most complex functions, like predicting eclipses with detailed notes on their expected color and direction, which were interpreted as omens. More importantly, the inscriptions give us a glimpse of the intended user. The text is explanatory, guiding, and educational. It doesn't assume the operator is an expert, but rather someone who needs instruction. This strongly suggests the mechanism was not a secret priestly tool, but a device for a scholar, a philosopher, or a teacher, used to demonstrate the orderly workings of the cosmos to students or patrons. In these faded letters, we hear the echo of the Hellenistic scientific community, a network of thinkers who saw the universe as a puzzle to be solved with mathematics and metal. The gears provided the motion, but the words provided the meaning, a direct transmission of knowledge across the vast silence of the centuries. This precise chronology turns the shipwreck into a time capsule. While the vessel carrying the mechanism sank between 70 and 60 years before the Common Era, the device it carried was not a new invention. Think of it like finding a modern shipwreck that contains a perfectly preserved, fully functional mechanical computer from the 1960s. The amphorae, the pottery, the coins, all these typical archaeological markers tell us when the journey ended, not when the journey of the idea began. To find the mechanism's true birth date, scientists had to look beyond the seafloor and into the stars themselves. The key was in the Eclipse cycle. Professor Mike Edmonds and his team realized the device's complex gearing was calibrated to a specific starting point. When they ran the astronomical math backwards, the cycle aligned perfectly with a date in 205 before the Common Era. This was not a random year, it was the anchor point for all its celestial predictions. Then came the handwriting analysis. Experts in ancient Greek script studied the thousands of tiny engraved letters on the bronze plates. The specific style of the characters, their shapes and flourishes, acts like a typographical fingerprint. This paleographic evidence pointed consistently to a craftsman working in the late 2nd century before the Common Era, perhaps around 150 to 100 before the Common Era. So we have a compelling timeline. This technological marvel was designed and built, likely in a workshop on the island of Rhodes, several generations before it was ever placed on that ill-fated ship. It was already a decades-old masterpiece, a treasured object of immense value and sophistication when it was lost to the sea. This fact is perhaps the most staggering of all. The Antikythera Mechanism was not a fluke, not a one-off experiment by a lone genius. It was a product of a mature and established scientific tradition, a tradition capable of producing such wonders as a matter of course. This realization forces a haunting question. If this was what they were capable of creating and casually transporting across the Mediterranean, what other marvels of that tradition have been lost to us forever, leaving not even a rusted gear behind? The ship that carried this wonder was no ordinary vessel. It was a floating treasury, a colossal Roman freighter perhaps 40 meters in length, originally built to haul grain across the Mediterranean. But on its final voyage, its hold held a different kind of wealth. Alongside the corroded gears of the mechanism lay a breathtaking collection of plundered beauty. There were life-sized bronze statues, their forms frozen in athletic grace, like the famous Antikythera youth with his poised, contemplative stance. There was delicate glassware that had survived the crushing depths, jewelry, silver coins, and marble sculptures. This cargo was not random trade goods. It was a targeted collection of Greek art and luxury, a museum on the waves. The historical context here is critical. By the 1st century before the Common Era, Rome had completed its military conquest of the Greek world. But as often happens, the conqueror became captivated by the culture of the conquered. A craze for all things Greek swept through the Roman elite. They didn't just admire Hellenistic art and philosophy, they demanded to possess it. This created a booming, brutal trade. Entire workshops, libraries, and temples were stripped of their treasures to decorate the villas and forums of a rising Italian power. The Antikythera ship was a direct participant in this cultural transfer. It was likely sailing from a major Greek intellectual center, possibly the island of Rhodes, which was renowned for its school of astronomy and engineering, heading west toward Rome when the storm took it. The mechanism's presence among statues and silver is profoundly telling. It wasn't hidden away as some secret device. It was packaged and transported as a prized object of prestige and knowledge, a luxury item for a discerning Roman patron who valued sophisticated Greek science. This reframes the mechanism completely. It wasn't a forgotten relic in a Greek temple. It was cutting-edge technology in transit, a symbol of status being delivered to a new world. Its loss in the shipwreck, then, represents more than just a sunken artifact. It marks the interruption of a specific moment in history, the very point where advanced Greek astronomical knowledge was physically being carried into the Roman sphere. We are left to wonder what influence might this one device have had if it had reached its destination. Could its intricate model of the cosmos have inspired new thinkers in Rome, accelerating the spread of these ideas? Its silence on the seafloor meant that a particular thread of technological progress was severed, leaving the world to rediscover its principles more than 1,000 years later. The search for the Creator leads us to a golden age of intellect, the Hellenistic world. In the wake of Alexander the Great's conquests, Greek culture and science exploded outward, mixing with the knowledge of Egypt and Mesopotamia to create an unprecedented hotbed of innovation. This was an era that believed the universe was governed by mathematical law, and they built machines to prove it. Two names rise above all others as potential architects of the mechanism's design. The first is the legendary Archimedes of Syracuse. Ancient texts describe him constructing a celestial globe, a moving model of the heavens so exquisite it was said to show the motions of the sun, moon, and planets. When the Roman general Marcellus sacked Syracuse, he reportedly took only two things as personal plunder: a set of mathematical instruments and this very device. Could the Antikythera Mechanism be a descendant of that lost Archimedean invention, perhaps built by followers carrying on his work? The second, and perhaps more compelling candidate, is Hipparchus of Rhodes. Working in the 2nd century before the Common Era, Hipparchus was arguably the greatest observational astronomer of antiquity. His revolutionary contribution was the theory of lunar anomaly, the precise mathematical model for the moon's subtle speeding up and slowing down in its orbit. This is not just a feature of the Antikythera mechanism, it is its mechanical heart, perfectly replicated by that astonishing differential gear. The correlation is too exact to ignore. The device physically embodies the very theories Hipparchus was developing at that time on the island of Rhodes. And Rhodes itself provides the final, crucial piece of the puzzle. The island was a renowned center for both astronomy and advanced engineering, a place where scholars and master metalworkers likely collaborated. The shipwreck's location on a major trade route from Rhodes to Rome makes this origin story deeply plausible, but to focus solely on a single famous name might miss the larger, more profound truth. The mechanism is a fusion of knowledge, blending centuries of precise Babylonian astronomical data with elegant Greek geometrical theory. Its construction required a master astronomer to design the math, a brilliant engineer to translate that math into bronze gear trains, and a supremely skilled artisan to cut the teeth and engrave the tiny, perfect letters. This speaks not of a lone genius toiling in isolation, but of a school, a workshop tradition where such collaborative marvels were possible. The Antikythera Mechanism, therefore, is likely not the signature of one man, but the masterpiece of an entire intellectual culture, a culture whose depth we are only now beginning to grasp as its sole surviving wonder slowly gives up its secrets. Yet this Greek masterpiece speaks with a Babylonian accent. The secret to its most awe-inspiring feat, the prediction of eclipses, lies not in the geometry of the Aegean, but in the mud-brick libraries of ancient Mesopotamia. For centuries, Babylonian astronomer priests meticulously recorded the movements of the heavens on thousands of clay tablets. Their goal was not pure science, but divination, believing celestial events were messages from the gods about the fate of kings and empires. Through this relentless observation, they uncovered a profound pattern, the Saros cycle. They noticed that every 18 years, 11 days, and 8 hours, the sun, moon, and earth returned to nearly the same relative alignment, making a similar sequence of eclipses possible again. This was a monumental discovery born from patient data collection over generations. When Alexander the Great's conquests opened the gates between East and West, this treasure trove of empirical data flowed into the Greek world. Scholars like Hipparchus pored over these Babylonian ephemerides, tables of numbers detailing planetary positions and eclipse timings. The Greeks, with their passion for underlying theory and geometrical models, took this raw data and sought to explain the why behind the Babylonian what. The Antikythera Mechanism is the breathtaking fusion of these two great traditions. It takes the Babylonian Saros cycle and literally engraves it in bronze. One of its spiral dials is a physical manifestation of this 18-year period, its pointer slowly advancing to mark each upcoming eclipse season. The device automates calculations that would have required a scholar to spend hours with clay tablets and a stylus. With a few turns of a crank, it synthesizes centuries of Mesopotamian observation with Greek mechanical genius. This transforms the mechanism from a national wonder into an international landmark. It proves the ancient Mediterranean was a connected intellectual network, a precursor to our own global scientific community. Data, theory, and craftsmanship traveled along trade routes with spices and silk. The device is a silent diplomat, speaking the universal language of mathematics, a testament to what humanity can achieve when knowledge is shared, not hoarded. It begs a reflective question: how many other breakthroughs in history have been born from this beautiful, fragile collaboration between cultures? But this brilliant synthesis of knowledge proved terrifyingly fragile. The most haunting question is not how the Greeks built such a device, but why its revolutionary technology simply vanished from the historical record for over 1,500 years. Its principles were not improved upon, they were completely forgotten, as if the spark of that idea was extinguished by the tides of history. Several converging factors likely led to this profound silence. The political world the mechanism knew was crumbling. The Roman Republic, which had created the demand for such luxury goods, was collapsing into a series of civil wars, a period of immense instability that disrupted trade, patronage, and the safe passage of ideas. Later, the slow fracture and eventual fall of the Western Roman Empire shattered the very economic and social structures that supported specialized, elite workshops. Crafting a device like the Antikythera Mechanism required not just a genius designer, but a network of highly skilled bronze casters, precision gear cutters, and expert engravers, all supported by wealthy patrons. That delicate ecosystem evaporated in an age of conflict and contraction. At the same time, a profound shift was occurring in how people understood the universe. The Hellenistic focus on mechanical, mathematical models of the cosmos gradually gave way to different priorities. Later Roman and then medieval scholarship often turned toward philosophical or theological explanations for celestial events, seeking meaning in the heavens rather than seeking to replicate their motion with gears. The intricate clockwork model may have come to be seen as a curious toy or even an impious attempt to mechanize the divine. Perhaps the most poignant theory is also the simplest: the knowledge was simply too concentrated. This was not mass-produced technology, it was bespoke artistry. The understanding of how to translate complex astronomical cycles into precise gear ratios may have been held by only a handful of master craftsmen in a single workshop tradition, possibly on Rhodes. Their expertise was a living library, passed from teacher to apprentice through hands-on work. If that chain was broken by war, economic hardship, or the passing of a master without a successor, the entire art could die in a single generation. The Antikythera Mechanism thus stands as a powerful, sobering symbol. It shows us that technological progress is not a guaranteed upward climb. It can be a fragile flame dependent on stable societies, open intellectual exchange, and the careful transmission of very specific skills. This one artifact whispers of an alternate path history did not take, a path where the analog computer age began not in the 19th century, but before the birth of Christ. Its silent gears ask us to consider what other bright sparks of human ingenuity in our own time or in ages past might have flickered and gone out, leaving no trace behind for us to find. The corroded bronze finally met its match in the invisible light of a new age. For decades, the mechanism's secrets were locked behind a stony crust, defying every traditional method of examination. Then, in the 1970s, a physicist named Derek de Solla Price teamed up with a Greek radiologist, Charalampos Karakalos, to attempt something unprecedented. They brought the fragile fragments to a nuclear research center and bombarded them with gamma rays. The resulting images were a revelation. For the first time, scientists could see the ghostly outlines of interlocking gear wheels deep inside the calcified mass, confirming it was a machine of astonishing complexity. This partnership between a historian of science and a medical imaging expert set the template for everything that followed, proving that unlocking this ancient puzzle would require the most advanced tools of the modern world. The true breakthrough, however, arrived with the dawn of the 21st century. An international team called the Antikythera Mechanism research project employed a technology straight out of a hospital: microfocus X-ray computed tomography. Imagine a medical CT scanner, but one so precise it could map the internal structure of the fragments in slices thinner than a human hair. This was archaeology without a single destructive touch. The scanner peered through centuries of corrosion like it was glass, revealing gears previously hidden from view, and most importantly, bringing to light thousands of Greek letters that had been utterly invisible on the surface. The inscriptions, now crisp and readable in 3 dimensions, provided the literal instructions for how the device was meant to be used, but seeing the pieces was only half the battle. The next step was to make them move again, not in bronze but in the digital realm. Researchers used the precise data from the scans to build intricate 3-dimensional computer models of every surviving fragment. They could then digitally reassemble the gear trains, testing how the teeth meshed and how motion would have flowed from the input crank to the various output dials. This virtual reconstruction allowed them to experiment, to test theories of missing components, and to simulate the device's operation with a fidelity that physical handling could never allow. It revealed, for instance, the brilliant double-layer design of some gears and confirmed the complex gearing needed for planetary motions. This ongoing investigation is a remarkable loop across time. 21st century computer scientists and mechanical engineers now collaborate with philologists and astronomers, using software and particle accelerators to decode the work of 2nd century before the Common Era metalworkers and mathematicians. Each modern scan, each digital simulation, is a conversation with the original creators. We are using our most sophisticated technology not to marvel at our own advancement, but to humbly recover a sophistication we once lost, piecing together a masterpiece of thought that has waited 2 millennia for an audience capable of understanding its full language. The digital blueprints created a new kind of alchemy, transforming data back into moving metal. Inspired by the precise scans and virtual models, master craftsmen and dedicated researchers around the world embarked on an extraordinary mission to build the machine again. These are not mere display pieces, they are working experiments in historical engineering, each turn of their gears a test of our modern understanding of an ancient mind. One of the most celebrated physical reconstructions came from Michael Wright, a former curator at London's Science Museum. His meticulous brass replica, built over many years, was the first to incorporate a working model of the planets, proving that the complex, looping paths of Venus and Saturn could indeed be replicated with the kind of gearing the Greeks possessed. Watching Wright's model in motion is a revelation as delicate pointers glide across finely engraved dials, tracking celestial cycles with a quiet, mechanical certainty. Across the world, another team from the Aristotle University of Thessaloniki took a different approach. They crafted their replica using modern materials like clear acrylic and precision-cut metal, making the internal gear trains visible. This transparent design allows anyone to see the beautiful, synchronized dance of the mechanism's heart, watching as the motion from a single hand crank branches out to drive multiple astronomical displays simultaneously. These physical models serve a crucial scientific purpose. They resolve debates. By building the gear trains exactly as proposed from the fragments, researchers can instantly see if the teeth mesh smoothly or if the calculated ratios produce the correct movements on the dials. A theory that looks perfect on a computer screen can fail in 3 dimensions, and these tangible replicas are the final, unforgiving test. Yet the wonder of the Antikythera mechanism is no longer locked in a museum workshop or a university lab. Interactive digital replicas now exist online, allowing anyone with an internet connection to manipulate a virtual version of the device. You can turn the crank yourself, watch the moon's phase wheel rotate, and see eclipse predictions align, democratizing access to this 2,000-year-old computer. These reconstructions, both physical and digital, are far more than copies. They are bridges across time. They transform silent, calcified fragments into whirring, ticking life, letting us experience not just what the mechanism was, but what it did. In the motion of these modern gears, we finally hear the physical echo of the ancient calculation, a whisper from the past that says, "You understand." For most of the 20th century, the mechanism was a ghost in the museum, a strange footnote known only to a handful of specialists. It was a puzzle without a solution, and so it languished in the quiet backwaters of academia. That all began to change with a single, groundbreaking article in Scientific American in 1959. Written by the historian of science Derek de Sulla Price, it carried a title that dared to redefine the artifact, an ancient Greek computer. To call a 2,000-year-old device a computer was a radical, almost heretical act. It forced the public to look at the ancient world through a completely new lens, not as a time of simple tools and superstition, but as an age capable of abstract mechanical thought. Price's work planted a seed, but it would take the visual proof of the 21st century scans for that seed to explode into the public consciousness. When those first 3-dimensional X-ray images were released, showing the intricate gear trains with crystal clarity, the story broke from the science journals and captured the global imagination. Here was undeniable, beautiful proof. The narrative was irresistible, a futuristic device found in a 2,000-year-old shipwreck. It became the perfect story for our digital age, a real-life precursor to the very computers that were now being used to decode it. Documentaries from major networks rushed to tell the tale, their cameras zooming in on the fragile fragments and the stunning animations of how it once worked. Museums around the world, from Athens to New York, created dedicated displays, often with working replicas visitors could interact with. The mechanism even leaped from history into fiction, inspiring plot points in novels and television series, where it often appears as the ultimate ancient secret, a symbol of lost advanced knowledge. This journey from obscurity to icon has done more than just make the device famous. It has fundamentally reshaped how we see antiquity. For generations, the popular view of the ancient Greeks was one of philosophers in togas and sculptors in marble, a civilization of art and words, not of engineering and precision machinery. The Antikythera mechanism shatters that simplistic image. It forces us to confront a Hellenistic world that wasn't just philosophizing about the cosmos. It was building precise mechanical models to simulate it. This realization is a powerful antidote to what scholars call chronological snobbery, the arrogant assumption that earlier cultures were inherently less intelligent or sophisticated than our own. The device stands as a permanent corrective, a bronze and gear declaration that scientific brilliance is not the sole property of the modern era. It proves that the ancient world could, in specific, breathtaking ways, rival the technical ingenuity of the Renaissance or even the early industrial age. Its story teaches a profound humility. We did not invent the concept of high technology, we merely rediscovered it, and in doing so, we are reminded that the spark of human genius can flare with astonishing intensity in any epoch, only to be dimmed by time, waiting patiently in the dark for its light to be seen again. The Antikythera Mechanism was not the only spark of advanced thought in the ancient world. To truly appreciate its place in history, we must look at the technological landscape from which it emerged, a landscape dotted with other ingenious inventions that hint at a world far more mechanically curious than we often assume. Consider the mysterious clay jars found near Baghdad, dating to the Parthian period around 200 years before the Common Era. These artifacts, often called the Baghdad Battery, consist of a ceramic pot, a copper cylinder, and an iron rod. When filled with an acidic liquid like vinegar or wine, they produce a small electrical charge. While scholars debate their exact purpose, whether for electroplating metals or perhaps for ceremonial sensation, they demonstrate an empirical understanding of basic electrochemical principles centuries before such concepts were formally defined. Then there is the brilliant work of Hero of Alexandria, a Greek engineer in the 1st century of the Common Era. He described and built the eolipile, a sealed sphere mounted on a boiler. When the water boiled, steam shot out from 2 bent nozzles, causing the sphere to spin rapidly. This was in essence a rudimentary steam turbine, a clear grasp of action and reaction, yet it was treated as a fascinating temple wonder or a philosophical toy, not as a source of practical power. We see similar sophistication in timekeeping. The Tower of the Winds in Athens, built in the 1st century before the Common Era, was an elaborate public clock tower. It used a complex hydraulic system, a water clock, to drive mechanisms that likely showed the time, the phases of the moon, and the positions of the sun and planets. It was a monumental, stationary computer for the entire city to see. Each of these devices showcases a different facet of ancient technical prowess, from harnessing chemical energy to utilizing steam pressure to automating public information. Yet when placed beside the Antikythera Mechanism, a critical distinction emerges. The Baghdad Battery is a simple cell, the eolipile a demonstration of a single principle, and the Tower of the Winds a large, fixed installation. None possess the Antikythera's breathtaking integration. It is a miniaturized portable system of at least 30 interlocking gears, performing multiple, simultaneous astronomical calculations with differential precision. It is not a demonstration of a force, but a dedicated, programmable simulation of cosmic order. This comparison does not diminish these other wonders, rather, it elevates the mechanism to its rightful place. It existed within a vibrant continuum of Hellenistic engineering that actively explored automation and mechanical marvels. But it represents the absolute pinnacle of that tradition, a fusion of abstract mathematics, precise craftsmanship, and profound cosmological understanding into a single, self-contained device. For sheer computational complexity aimed at modeling the universe, it stands utterly alone in the archaeological record, a solitary peak whose height would not be matched for over a millennium. Even with our most advanced scans and brilliant reconstructions, the mechanism remains an incomplete manuscript. We have deciphered many of its chapters, but entire pages are still missing, lost to the sea or hidden within the remaining, unreadable crust. The most tantalizing blank spaces revolve around its full physical form and its ultimate purpose. While our models show a compact, book-sized device, some researchers propose the original may have been larger, perhaps even mounted within a more elaborate case that displayed its dials like a miniature orrery for an audience. The gears for the planets, particularly Mars and Venus with their complex loops, are a ghost in the machine, strongly implied by the inscriptions and the empty spaces in the gearing, but not yet confirmed by physical evidence. Each missing gear is a silent question. How was this marvel actually used? Was it a philosopher's demonstration tool, a wealthy patron's conversation piece, or an astrologer's practical reference? The inscriptions suggest a pedagogical function, a device to teach the mathematical harmony of the cosmos. Yet its precise eclipse predictions, complete with omens about wind and kingship, also tie it directly to the astrological practices of the era. It likely served all these roles at once, a single object reflecting the intertwined nature of science, education, and belief in its time. The true daily life of the mechanism, the hands that turned its crank and the eyes that followed its pointers, remains just out of focus, a vivid scene we can only partially reconstruct. The quest for answers has now returned to where it all began, the dark seabed off Antikythera. A modern international mission called the Return to Antikythera project has taken up the challenge, armed with technology the original sponge divers could never have dreamed of. Their divers wear exosuit-hard suits that function like personal submarines, allowing them to work safely at great depths for hours. They deploy robotic mapping vehicles and precise suction dredges to systematically excavate the site, treating it with the care of an archaeological dig on land. This renewed investigation has already yielded stunning finds that broaden the story of the shipwreck itself, from a magnificent bronze spear that once belonged to a larger-than-life statue to delicate glassware and pieces of fine furniture. But for those fascinated by the mechanism, the most electrifying discovery came in 2018. The team recovered a flat, circular bronze disc, about 8 centimeters across, heavily corroded but clearly worked by human hands. Most intriguingly, it bears the image of a bull. Experts immediately recognized a potential connection. The bull is the symbol for the constellation Taurus. Could this disc be a missing dial face from the original Antikythera mechanism, or perhaps even a component from a second, similar device on the same ill-fated ship? The possibility is breathtaking. It suggests that the mechanism on display in Athens may not have been unique, that it could have been one of several produced by a skilled workshop. Each new dive is now a high-tech treasure hunt, not for gold but for knowledge. Every lump of encrusted bronze hauled to the surface is placed gently in a freshwater tank, where conservators will spend years patiently cleaning it, millimeter by millimeter, hoping to find the telltale glint of a gear tooth or the curve of an engraved Greek letter. This is the enduring power of the Antikythera mechanism. Its story is not a closed book. It is a narrative that continues to unfold in real time, written by oceanographers scanning the murky depths, by conservators peering through microscopes, and by programmers running new simulations. The deep sea still guards its final chapters, and with each passing season we develop better tools to read them. What we have already learned has irrevocably changed our view of history. What we have yet to find could change it all over again. The dials could predict an eclipse down to the hour, but they also foretold its color and the direction of the winds that might follow. This single function captures the central tension surrounding the mechanism's purpose. Was it a brilliant scientific calculator or an elaborate astrological guide? For the modern mind, these seem like opposing uses, but to the ancient Greeks who crafted it, such a distinction would have been meaningless. Astronomy and astrology were two sides of the same coin, a unified study of the sky. The mechanism's designers sought to understand the rules, and those rules were believed to govern everything from the tides to the fate of nations. The detailed inscriptions naming constellations and star phases provided the raw data for both pursuits. A philosopher could use the same pointer position to lecture on lunar orbital theory, while a temple priest could use it to determine the most auspicious day for a city's important ceremony. The device did not choose between science and belief. It served both with impeccable mechanical accuracy. Consider the evidence for its role as an educational instrument. The thousands of explanatory Greek letters are not cryptic codes. They are clear labels and instructions. This suggests an audience that needed guidance, perhaps students in a philosophical school like the Stoics or the followers of Aristotle, who saw the cosmos as an orderly system. Turning the crank and watching the synchronized dance of the sun and moon pointers would have been a powerful demonstration of celestial harmony, a physical proof of mathematical law. It transformed abstract theory into tangible, moving reality. In this light, the mechanism was a revolutionary teaching aid, a portable planetarium that made the complex principles of Hellenistic astronomy accessible and awe-inspiring. Yet the same gears that taught geometry also served prophecy. The most compelling astrological feature is the Saros dial, the spiral track that predicted eclipses. In the ancient world, an eclipse was a moment of profound dread and potential. Kings and generals anxiously consulted seers about their meaning, believing these events could signal the fall of a ruler or the outcome of a coming battle. The mechanism's ability to forecast these events years in advance would have been a source of immense power and prestige. Furthermore, by modeling the positions of the planets against the zodiac, the device could generate the basic celestial snapshot needed to cast a horoscope for a specific moment, like a birth or a coronation. This wasn't seen as superstition, but as applied cosmic knowledge, using the best available science of the day to navigate a world believed to be intimately connected to the heavens. So we must let go of our modern categories. The Antikythera Mechanism was not one or the other. It was both entirely and without contradiction. It represents a holistic worldview where observing a planet's retrograde loop was simultaneously a mathematical puzzle and a message about human affairs. The genius of its creators lay in their ability to build a machine that satisfied this complete hunger for understanding. It catered to the intellect's desire for order and the spirit's search for meaning, all through the exquisite turn of a bronze gear. This duality makes it not less scientific but more human. It reflects a culture that sought to grasp the universe in its entirety, using every tool at its disposal, from precise observation to poetic interpretation. In its silent computation, we find the echo of an age that dared to ask not just how the heavens moved, but what they meant to those living in their light and shadow. The true genius of the mechanism lies in its mathematics, but its physical reality is a testament to an equally profound mastery of materials. To hold this device was to hold a symphony of choices, each one revealing the sophisticated engineering mind of its maker. The gears themselves are not made from just any bronze. Scientific analysis shows they were cast from a specific alloy, a low tin bronze. This was a deliberate selection. Too much tin makes bronze hard but brittle, prone to cracking under the stress of interlocking teeth. Too little tin makes it soft and easy to wear down. The chosen formula struck the perfect balance, offering just enough hardness to hold a sharp edge for those minuscule teeth, yet enough malleability to be worked, filed, and adjusted after casting. It was a material engineered for both precision and longevity. This metallurgical knowledge didn't appear by accident. It was the accumulated wisdom of centuries of metalworkers, applied here to solve a novel problem: how to build a reliable, miniature cosmos that could turn for generations. The gears were housed within a wooden case, now long since returned to the sea, likely made from a fine-grained, stable wood like oak or boxwood. This choice speaks to the device's purpose as a treasured object, something meant to be handled, displayed, and protected. The wooden frame would have provided a rigid structure for the delicate bronze clockwork, insulating it from shocks and perhaps even featuring beautifully carved panels, turning the mechanism into a work of art both inside and out. But the most staggering evidence of skill is found at the smallest scale. Look closely at the surviving gears. Their teeth are not crude, hand-filed approximations. They are uniform, with near-identical triangular profiles and remarkably consistent spacing. Some of these teeth are just over a millimeter in length, a size that challenges even modern machinists working without electric tools. This level of repeatable precision did not happen freehand. It implies the use of specialized tools, what we would call jigs or templates. The artisan likely had a dividing plate, a circular guide marked with degrees or tooth positions, to ensure each gear blank was indexed perfectly before cutting. They would have used fine, needle-like files, perhaps mounted in a simple lathe or bow-driven drill to achieve a smooth, even cut. The tiny Greek letters, thousands of them, were not scratched onto the surface but engraved with a berin, a sharp, chisel-like tool, guided by a steady hand and a deep understanding of the script. Each letter is a masterpiece of micro-calligraphy. To envision the workshop where this was created is to step into a unique intersection of disciplines. In one corner, a metallurgist tends a clay crucible, carefully monitoring the color of the molten bronze to judge its tin content. At a bench, a mathematician consults complex astronomical tables, translating celestial cycles into numerical gear ratios. And at the heart of the room, the master artisan, a person who is both engineer and artist, uses their array of specialized tools to transform these abstract numbers into tangible, interlocking bronze reality. The air would have smelled of hot metal, wood shavings, and the oil used to lubricate the cutting tools. The sound would have been a quiet, focused symphony of scraping, tapping, and the gentle hum of a bow drill. This was not a blacksmith's forge producing tools or weapons. It was a precision instrument shop, a place of quiet concentration where the goal was not strength, but perfect, predictable motion. The scale of the work forces a complete reconsideration of the ancient toolkit. We often picture the classical world with chisels, hammers, and looms, but the Antikythera Mechanism demands we add precision gear cutters, engraving berins, and measuring calipers to that mental image. It speaks of a culture that valued minute accuracy, that had developed the techniques to achieve it, and that applied this painstaking skill to the grandest subject imaginable, the universe itself. The patience required is almost beyond comprehension, each tooth, each letter representing hours of focused labor, all in service of a single, unified vision. In these silent, corroded fragments, we do not just see a machine, we witness the quiet, patient expertise of hands that have been still for 2,000 years, hands that believed the order of the heavens was worth capturing in metal. This single artifact rewrites the timeline of human ingenuity. Before its discovery, the history of complex geared machinery followed a well-worn path. Scholars traced it from the great astronomical clocks of medieval Europe, like the one in Prague from the 1400s, back through simpler water clocks of the ancient world. The Antikythera Mechanism shatters that timeline completely. It proves that the conceptual leap from writing down mathematical theories to building a physical machine to simulate them did not happen in the Renaissance or the Islamic Golden Age. It happened in the workshops of the Hellenistic world over 1,000 years earlier. This is not just moving a date on a chart, it is redefining an entire chapter in the story of science. The mechanism stands as a brilliant, lonely beacon of a technological path that was almost entirely lost. For centuries, the dominant narrative held that the ancient world excelled at philosophy, sculpture, and architecture, but not at precision mechanical engineering. This device forces us to confront a different reality, one where a culture deeply invested in understanding cosmic order also possessed the technical skill to model that order in moving bronze. It suggests a parallel stream of innovation focused not on power, like water mills or siege engines, but on information, on analog computation. This lost path was concerned with encoding knowledge into machinery, a pursuit that would not be seen again on such a sophisticated scale until the geared astrolabes and clocks of the later medieval period. In that light, the intricate clock towers of Europe are no longer sudden miracles of invention. They become part of a rediscovered tradition, perhaps even distant echoes of a knowledge that had traveled, fragmented and diluted, through surviving texts or rare artifacts, inspiring craftsmen centuries later. The mechanism thus fills a profound gap in our historical understanding. It provides a missing link, a tangible precursor that makes the later flourishing of mechanical science feel less like a spontaneous birth and more like a reawakening. This transformation reaches its fullest expression when we reconsider the very origin of the computer. The standard genealogy often begins with Charles Babbage and his visionary steam-driven difference engine in the 1800s, a device designed to automate mathematical tables. But the Antikythera mechanism demands we extend that lineage back by 2 millennia. While Babbage's machine was digital, designed for calculation, and the Greek device was analog, designed for simulation, they share a foundational ambition to use precisely arranged metal components to automate complex intellectual tasks. They are both, in essence, computers. One is powered by steam and punch cards, the other by a hand crank and celestial mathematics. Recognizing this connection creates a much longer, richer, and more humbling lineage for our own digital age. It places the spark of computational thinking not in the smokestacks of the Industrial Revolution, but in the clear, starlit skies of the ancient Mediterranean. The mechanism's legacy, therefore, is not merely as a fascinating oddity. It is a corrective to a narrow view of progress. It reminds us that scientific and technological advancement is not a straight, inevitable line upward, but a fragile and often branching tree. Some branches grow strong and define an era, while others, like the one that produced this bronze cosmos, are pruned back by the storms of history, leaving only a single, miraculous seed to be found much later. In that seed, we see the full potential of a path not taken, a silent question about what our world might have learned if this ancient computer had never been silenced by the sea. The journey from a shipwreck silt to a museum's spotlight is now complete. Today, you can stand face to face with the original fragments of the Antikythera mechanism. They reside in a quiet, purpose-built room at the National Archaeological Museum in Athens, a space designed to protect these delicate pieces of bronze from the passage of time they have already so miraculously endured. The fragments are arranged in a special climate-controlled case, illuminated with a soft, respectful light that highlights every curve of corrosion and every faint glint of ancient metal. Surrounding the originals, you will often find working replicas made of gleaming brass or clear acrylic, their gears turning in a silent demonstration of what the silent lumps once accomplished. Interactive screens allow visitors to manipulate a digital model, to set a date and watch the pointers align, bridging the gap between the static artifact and its dynamic purpose. This careful presentation transforms the museum visit from simple observation into a multi-layered conversation across millennia. But the mechanism's story is no longer confined to Greece. Recognizing its global significance, major international exhibitions have carefully transported select fragments to museums across the world. Institutions like the Archaeological Museum in Basel and the Leonardo da Vinci Museum of Science and Technology in Milan have hosted these extraordinary displays. The lines to see these exhibitions are consistently long, a testament to a shared, profound curiosity. People are not just looking at an old piece of metal, they are seeking a tangible connection to a specific moment in our collective past when human thought achieved something breathtaking. This global fascination points to a deep, universal human trait, a sense of awe when we are confronted with unexpected sophistication from our ancestors. It challenges a subtle, often unspoken assumption that people in the distant past were less capable, less intelligent, or less innovative than we are. To see the Antikythera mechanism in person is to have that assumption quietly dismantled. There is a powerful, almost humbling experience in observing the actual palm-sized fragments resting behind their glass. You are not looking at a picture or a reconstruction. You are standing before the very object that a philosopher or a sailor might have held, that sank to the bottom of the sea for 2,000 years, and that now speaks a silent, potent language of mathematics and ambition. It creates a direct, personal bridge across an immense gap in time, linking your modern wonder directly to the ancient minds that conceived it. In that quiet museum room, surrounded by the whispers of other visitors from every corner of the globe, the mechanism performs its final, most elegant calculation. It measures the enduring reach of human genius and finds the distance to be far shorter than we ever imagined. The story of this ancient computer is not owned by any single university or museum. It has been pieced together just as much by hands working in home workshops and minds coding in spare bedrooms as by those in formal laboratories. While major research teams with their advanced scanners provided the crucial data, the task of interpreting that data, of testing theories with physical models, has been passionately taken up by a global community of amateurs. These are hobbyist machinists with lathes in their garages, freelance programmers skilled in three-dimensional animation, and independent historians with a deep love for ancient technology. Their contribution is not a footnote, it is a fundamental chapter in the mechanism's modern rediscovery. Consider the challenge of building a working replica from the published scans and measurements. This requires translating two-dimensional blueprints into three-dimensional moving parts, solving practical problems of alignment and friction that a pure theorist might overlook. Amateur machinists around the world have done exactly this, crafting beautiful, functional models from brass and steel. Each successful gear train they assemble, each smoothly turning dial, serves as a physical proof of concept for a proposed interpretation of the ancient design. Their work is a form of experimental archaeology, where a theory is only proven when the metal teeth mesh without binding. Online, this collaboration has exploded. Dedicated forums and open-source software projects have become digital workshops where enthusiasts from every continent gather. A programmer in California might share a new simulation of the planetary gearing, which a retired engineer in Germany can critique based on their own gear calculations, while a student in Greece cross-references the findings against the latest academic paper. Ideas are proposed, tested in code, debated, and refined in a vibrant, decentralized conversation that runs 24 hours a day. This crowd-sourced approach has led to genuine innovations, such as novel proposals for the layout of lost gear trains that even professional teams have found worthy of consideration. What we are witnessing is a new model for solving ancient mysteries. The Antikythera Mechanism, with its blend of astronomy, history, and precision engineering, acts as a perfect intellectual puzzle, attracting problem solvers from countless disciplines who would never meet in a traditional academic setting. Their shared passion bypasses institutional walls, creating a living network of collective intelligence. This transforms the narrative from a simple tale of archaeological discovery into a modern parable about how knowledge is built in the Internet age. It demonstrates that profound historical understanding can emerge not just from the top down, but from the edges in, fueled by curiosity and enabled by global connection. The 2,200-year-old puzzle, in the end, is being solved by a 21st-century global village, proving that the human drive to understand our past is a force that can unite amateurs and scholars alike in a common, wondrous task. That single, silent artifact in its museum case quietly dismantles a comforting myth about history itself. We often imagine the human story as a straight line, a steady march from simple tools to complex machines, from superstition to science, with each generation standing on the shoulders of the last. The Antikythera Mechanism shatters that linear narrative. It presents us with something far more profound and unsettling, the idea of cyclical loss. Here is a device that demonstrates a conceptual and technical sophistication that would not be seen again for over a millennium. Its existence proves that a civilization can reach a dazzling peak of capability in one specific domain, only to have that knowledge vanish, as if swallowed by a historical tide, leaving future generations to believe they were the first to discover such principles. This forces a fundamental shift in how we view antiquity. We can no longer see the ancient Greeks or any past culture as merely a stepping stone to us. They were not primitive versions of ourselves, they were complete societies with their own unique constellations of knowledge, some of which burned brightly and then went dark. The mechanism compels us to ask a haunting question. If something this advanced could be completely forgotten, what else has been lost? What other libraries of Alexandria burned, not with fire, but with the simple passing of time and the breaking of a single chain of apprenticeship? Perhaps there were other devices, other theories, other ways of seeing the world that flourished briefly and then disappeared without leaving a single corroded gear behind for us to find. This realization is deeply humbling for our modern age of seemingly boundless innovation. Our entire technological confidence is built upon a foundation of preserved knowledge, a fragile inheritance passed down through manuscripts, artifacts, and living traditions. The mechanism stands as a stark monument to the fact that this inheritance is not guaranteed. It can be fractured. Specific, intricate skills, like translating lunar anomaly into a differential gear, can evaporate from human memory if the conditions that nurture them change. This invites a new kind of respect for the past, not as a quaint prologue, but as a landscape dotted with independent peaks of achievement. Some of those peaks, like Roman aqueducts or Gothic cathedrals, remain visible on our horizon. Others, like the knowledge that built this bronze computer, were mountains that eroded back into the plain, their contours forgotten until a chance storm revealed a single, astonishing stone. To understand the mechanism, then, is to accept a more complex and beautiful view of human history, one not of a simple climb, but of a journey through a terrain where brilliance can appear, fade, and reappear in unexpected places across the vast expanse of time. The deep blue waters off Antikythera are no longer a graveyard of scattered wonders, but an open-air library being carefully read page by page. Modern archaeology has returned to the shipwreck, not with heavy lifting cables and desperate dives, but with a surgeon's precision and a scientist's patience. The key to this new chapter is technology that would seem like magic to the original sponge divers. Teams now deploy autonomous underwater vehicles gliding silently over the site, their sonar and laser scanners building a three-dimensional map of the seafloor with centimeter accuracy. This photogrammetric model is a revelation, a digital twin of the wreck site that allows archaeologists to study every stone and contour without ever getting wet, to plan their next move with the care of a chess master. But when it is time to interact with the past, humans still enter the water, encased in a different kind of marvel. The exosuit is a robotic diving system that looks like something from a science fiction film. A hard metal suit that allows a researcher to descend to the wreck and work at depth for hours without the dangers of decompression sickness. It is essentially a personal submarine with robotic claws that can perform delicate tasks under direct human control. This combination of remote mapping and hands-on precision has enabled the first true systematic excavation of the site in over a century. The process is slow, meticulous, and fundamentally different from the treasure hunts of the past. Every scoop of sediment is carefully sifted, not for gold but for data. Tiny fragments of wood, a single corroded coin, a broken pottery shard, these are the words of the story. The goal is to understand the context, to see not just what was on the ship, but how it was stored, what was beside what, and what that arrangement can tell us about the ship's origin, its cargo, and the lives of those on board. This is archaeology where preservation is the highest principle. Every artifact recovered, from a massive bronze statue arm to a sliver of eggshell-thin glass, is immediately placed in a freshwater conservation tank to slowly leach out the corrosive salts accumulated over 2 millennia. The work is a race against a different kind of clock, the clock of degradation, ensuring these objects survive their journey from the seafloor to the museum for future generations to study. While the dream of finding another gear from the mechanism drives much of the public fascination, the archaeologist's mission is broader. They seek to reconstruct the vessel itself, to analyze the amphory to trace its trade route, to study the personal items that might speak of the crew's daily lives. Each dive adds another sentence to the biography of this lost ship. The modern legacy of the Antikythera Mechanism, therefore, is not just a rewritten history book, but a new standard for how we respectfully recover our shared past from the deep, treating each site not as a trove to be plundered, but as a fragile, submerged chapter of the human story, waiting to be read with the light of careful science. The true legacy of the Antikythera Mechanism is not locked in a museum case. It lives in the questions it forces us to ask about our own creations. For modern engineers and innovators, this 2,000-year-old device offers profound, practical lessons that cut to the heart of how we design and build today. At its core, the mechanism is a masterpiece of elegant problem-solving. Its creators faced a monumental challenge: how to represent the irregular, mathematical dance of the cosmos using only bronze gears and a hand crank. They did not have silicon chips or software code. They had metal, geometry, and immense patience. Their solution was to translate abstract astronomical cycles into precise physical ratios, a tangible algorithm made of interlocking teeth. This teaches us that sometimes the most powerful solutions are not the most complex in terms of components, but the most ingenious in their simplicity of concept. It reminds us to look for the clean, mechanical essence of a problem before reaching for digital complexity. This leads directly to a second, vital lesson: the unparalleled power of interdisciplinary work. The mechanism could never have existed without a seamless fusion of distinct fields. An astronomer provided the celestial data and the mathematical models. A metallurgist formulated the perfect bronze alloy to balance strength and workability. A master craftsman possessed the tool-making and precision machining skills to cut minuscule, uniform teeth and engrave microscopic letters. This was not a lone genius in a garage. It was a collaborative workshop where different forms of expertise converged to create something greater than the sum of its parts. In our era of increasing specialization, the mechanism stands as a timeless argument for building bridges between disciplines, for creating spaces where theorists and makers can speak the same language. Perhaps the most striking lesson for our contemporary world is one of endurance. We live in an age of planned obsolescence and digital fragility, where devices are often designed to be replaced within a few years and where data can vanish with a failed hard drive or an outdated file format. The Antikythera Mechanism, by stark contrast, is a monument to robust, long-lasting design. Though shattered, corroded, and resting on the seafloor for 2 millennia, its core function remained decipherable. The information it contained was not stored in a fleeting magnetic charge, but in the immutable geometry of its gear trains and the physical engraving of its inscriptions. It challenges our throwaway culture and asks us to consider what it means to build for legacy, to create objects whose value and function can persist across centuries, not just product cycles. This ancient computer inspires us to look up from our digital screens and reconsider the enduring power of physical, mechanical ingenuity. There is a profound tangibility to a solution you can hold in your hand, whose workings you can trace with your eye and understand through the direct cause and effect of moving parts. In an increasingly virtual world, the mechanism reawakens an appreciation for the artistry of the physical, for the satisfaction of a problem solved not just in code, but in the real, enduring interaction of material and design. It whispers to the modern innovator that true advancement is not always about chasing the next new thing, but sometimes about rediscovering the timeless principles of elegance, collaboration, and resilience that allowed a bronze wonder to speak to us from the deep past, its message clearer now than ever before. The mystery of the bronze gears proved too compelling to remain confined to academic journals. It has seeped into the very fabric of our stories, becoming a modern icon of ancient enigma. You can find its influence on the pages of novels like Robert J. Staver's The Antikythera Codex, where its intricate workings unlock fictional secrets from a forgotten past. On television, it has been the star of its own documentaries, featured in profound episodes of series like Nova and Horizon, where scientists and historians piece together its puzzle for a captivated audience. But perhaps its most fascinating role is in the realm of fiction, where it frequently appears as a pivotal plot device. In these stories, the mechanism is often more than a relic. It becomes a key, a map, or a message from a more advanced civilization, either human or otherwise. These narratives thrive on the tantalizing what-if scenario the real artifact inspires. What if this device had not been lost? What if the knowledge it represented had continued to evolve? Could the Industrial Revolution have happened 1,000 years earlier? Or could humanity have developed a completely different relationship with technology? This cultural permeation reveals something beautiful about how we process discovery. The Antikythera Mechanism has transcended its archaeological origins to become a powerful symbol. It now stands for lost potential, for hidden histories, and for the thrilling possibility that the past holds surprises that can reshape our understanding of ourselves. It taps directly into a deep-seated human love for puzzles and the profound romance of a secret rediscovered. The very fact that this true story, with its real-life divers, X-ray scans, and ancient inscriptions, can generate as much wonder and speculation as the most imaginative fiction, is a testament to its power. It proves that reality, when it presents us with an object that seems to whisper from the wrong point on our timeline, can be the most compelling mystery of all. Yet the mechanism's journey from seabed to museum case is not just a scientific story, it is an ethical one. A single question lies at its heart: who truly owns this marvel? Legally and historically, it is unequivocally a national treasure of Greece, recovered from its waters and a direct product of Hellenistic culture. Yet its message about human ingenuity transcends any border, making its significance undeniably global. This creates a beautiful tension, a single object that belongs both to a nation and to all of humanity's shared history. Modern museums navigate this by striking a careful balance. The fragile, 2,000-year-old original is preserved under strict conditions, protected from light and air that would accelerate its decay, but its knowledge is set free. Through precise physical replicas and freely available digital scans, anyone, anywhere, can study its gearing or marvel at its function. This philosophy transforms ownership from possession into stewardship, where the primary duty is not to hide the wonder, but to safeguard it while sharing its story as widely as possible. This stewardship extends to the very site of its discovery. The Antikythera shipwreck is more than an archaeological trove, it is a final resting place. The skeletal remains found there remind us that this was a scene of profound personal loss. Modern excavations therefore proceed with a solemn respect, treating the site not as a treasure hunt but as a sacred space of memory. Every effort is made to document the context with care, understanding that the arrangement of artifacts can tell us as much about the people on board as the objects themselves. The ethics here are clear. The pursuit of knowledge must be guided by reverence for those who came before. Even the act of study presents a dilemma. To unlock the mechanism's secrets, researchers must sometimes use invasive techniques. While non-destructive imaging like X-ray tomography is ideal, sometimes a tiny sample must be taken to analyze the metal's composition, or a delicate cleaning process might risk damaging a fragile inscription. Each decision is weighed with immense care, a constant calculation between gaining new understanding and preserving the physical integrity of the artifact for future generations. There is no perfect answer, only a series of thoughtful compromises made by the conservators and scientists who serve as its current guardians. These are not abstract academic debates, they are living questions that shape how this ancient wonder is shared with the world. Every museum display, every research paper, every public lecture is part of an ongoing conversation about our responsibility to the past. The choices made today determine whether the Antikythera Mechanism remains a static relic behind glass or becomes a living inspiration, its gears turning not in bronze but in the minds of everyone who encounters its story. In this way, the device challenges us once more, asking what we value more, the object itself, or the spark of understanding it can ignite across centuries. The ultimate meaning of the Antikythera Mechanism may not be found in its bronze, but in the question that forged it. For as long as we have looked up at the night sky, we have sought to bring its vastness down to a human scale, to find patterns in the chaos and build tools to make sense of it all. This drive connects the standing stones of Stonehenge, aligned to the solstice sun, to the golden mirror of the James Webb Space Telescope, peering back to the dawn of galaxies. It is a continuum of wonder, and the mechanism is not an outlier but a breathtakingly sophisticated point on that very line. It proves that the desire to compute, to model, and to predict the cosmos is not a product of our Silicon Age. It is a fundamental, ancient strand of the human spirit. This object is a physical manifestation of the question, how does it work, asked with brilliant specificity over 2,000 years ago. In its carefully calculated gear ratios, we see the same intellectual ambition that fills a modern physics lab or a software engineer's screen, a relentless pursuit to translate observation into understanding. The anonymous Greek craftsman who filed each tiny tooth, guided by the mathematical theories of an astronomer like Hipparchus, was engaged in the same essential project as the scientist today who studies the device's fragments with X-rays and particle beams. They are collaborators across millennia, united by a shared compulsion to decode the universe's hidden language. The mechanism, therefore, is more than a relic, it is an emblem. It symbolizes the timeless conversation between our curiosity and the cosmos, a conversation conducted with stone circles, with bronze gears, and now with digital code. It reminds us that our greatest tools are not the materials we use, but the questions we dare to ask. The silent, corroded gears from that shipwreck do not just model the motions of the heavens, they mirror the enduring motion of the human mind itself, forever turning, forever seeking to grasp the magnificent clockwork of existence. That corroded lump of bronze is a conversation across 2,000 years. It speaks not of kings or conquests, but of quiet calculation and cosmic ambition. Our journey through its story, from a storm-lashed shipwreck to the quiet hum of a modern scanning lab, forces us to rewrite a chapter of history we thought we knew. This was not a primitive time awaiting our enlightenment. It was an era that built a portable universe with gears, a civilization whose grasp of mechanics rivaled that of the finest clockmakers a millennium and a half later. The Antikythera Mechanism is a permanent challenge to our assumptions. It asks us to look at every ancient culture with fresh eyes, to wonder not just at their art and philosophy, but at the sophisticated engineering that may have flourished and then vanished without a trace. This single artifact expands our respect for ancient ingenuity to a staggering degree. It proves that the spark of high technology is not a modern invention, but a recurring flame in the human story, one that can burn brightly, be smothered by the tides of time, and then be patiently rekindled by later hands. The true message from the past is one of humility and possibility. History is not a straight, predictable line. It is a landscape full of surprising peaks, some of which were worn down by time, leaving only a single, miraculous stone to mark their existence. The ongoing exploration of the shipwreck site promises that this story is still being written. With each dive, each new fragment recovered from the seabed, we add another sentence to this ancient manuscript. What final secrets might the deep still hold? Could another gear, another inscribed plate, or even evidence of a second device reshape the narrative once more? The sea has guarded its mysteries for 2 millennia, and it may not be finished yet. What do you think its final secrets will be? Share your thoughts in the comments below. And if you were fascinated by this journey through time, subscribe for more explorations into history's greatest mysteries.